Death, war, and destruction plagued humanity for the past millions of years. It was time to do something. Or at least, that's what the excuse was to make this project. We wanted to make something big and to showcase what we can actually make. After making all those previous mini projects, I personally wanted something mobile, something complex and revolutionary, which would bring all my past project experience and knowledge into one place, giving birth to something ultimate, which would not only be the best thing to look at and present to people, but also a technical feat for us. So yeah, we decided to make an automated mobile robot that can pathfind and 3D scan entire areas, can also give us informations like temperature, humidity and smoke levels, etc., which would be displayed eloquently in a software that we would develop, which not only aids the rescue team to better navigate the terrain, but also informs us in case of fire and smoke, along with its exact location. This digital twin can also be overridden with manual control, providing us with an efficient two-way communication system. We, along with SARDA, aim to change the way these rescue operations are approached in order to create a more healthy and safer working environment for rescue personnel and shape a better and more secure future ahead. Now, this whole system consists of 3 different units that would work together in harmony. The deployable locomotive unit, which is automated and has the capability to pathfind and traverse the terrain while scanning and mapping its surroundings. The captured data is sent to a receiver and controller unit, which further processes it and sends it to the attached computer, which has the virtual assistant installed. This renders the geometry and displays all the other data intelligently to the user. The dynamic virtual assistant consists the digital twin of the deployable unit and thus can be overridden and controlled passively. This makes the RCU capable of two-way communication. The separate receiver unit packs the system with versatility, where it can be used with any device, be it an Android, Windows, Linux, irrespective of the hardwares working alongside with each other. With all this in mind, we started working on the project. It was day 1. We brought all the necessary materials, stuffs needed to build the project. And hey, we tried to use an Arduino Nano, making it the first time we ever tried using one of these bad boys. All this was not enough, but surely it gave us a good starting point for the build. We would make everything from scratch, even the body of the robot. I would use my classic lamination fiber and that good old knife, as I did in my previous project, to make the chassis of the robot. And of course, I had my beloved Sayanti working with me in the New York University Robotics lab. We started by making and preparing the lamination fiber in order to cut them into shapes. Now, before we could even get started, we realized that 4 of the custom DC motors armature we brought would house the wheels of the car and help drive all of them individually. Didn't have wires or jumper cable attached to them, of course, and even though it was so obvious, it meant that we had to solder in our own wires, attach and prep them properly at first before we can even test them out. This was problematic for us because we must confess it's the first time we are picking up the soldering iron. Kids with big dream we are, huh? You know what we mean? There are first time for everything. This was a good opportunity to learn how to do a good old soldering. We stripped and prepared the jumper cables that we had in order to weld them to the motors and got the soldering equipments, including the paste and everything. It took a few blisters, some YouTube videos and a series of failure to get things up and running. And right when we thought things were done, the wires would come off. It took a lot of fiddling around to get it in a stable position. We even used hot glue to secure the wires in place and prevent short circuit. We were using the L239D motor driver, which was also new to us. So we had to look up the data sheets and articles on the web in order to learn all of its features and how we can use it to its fullest potential. Once we got it to work, we were finally able to attach the DC motors that we prepped by soldering together and test it out whether they work. But before we could move forward, another problem befell us. And it's because we couldn't find any data sheet or information on the operating voltage of the motor motor. Now that wasn't a dead end because we decided we'll go with 7.4 volt instead. That's 2 of our lithium ion batteries in a 3-slot battery holder. So we needed to connect 2 of the terminals together in order to skip 1 slot and make it work with 2 batteries instead of 3. Let's just say things didn't go well. Occasional disaster here and there due to short circuit and wrong polarities, but yeah, we brought in a multimeter and made it work eventually. With that done, we hooked up the DC motor and it worked perfectly as we steered towards the spinning wheels. In order to not mess things up, we made a rough 3D model of the whole robot. Here, the locomotive unit inside of 3D Studio Max with real-life measurements to figure out what the optimal size of different parts should be, and if we had to add something, we would just look up the dimension digitally and whether it would fit properly. So yeah, after we decided the structure and the measurements of the car, we used our good old carbon knife to cut out the fiber into the needed pieces. Now we were way past the amateur mistakes, we knew what to do. So the next step was to attach the different circuits and equipments on board before we take care of the motors. So we have to take in consideration the battery holder, the motor driver and the other equipments that would go on the board. So we measured all the different components and decided how much spare space we needed for it. Used the 3D Studio Max model as a reference and drew the line on the board where we needed to get holes for the screws instead of sticking them with glues which would come off eventually with harsh usage. So yeah, we spent a lot of time into the measurement aspect of the build and marked the fibers with carbon knife. We overlaid the different modules onto the fiber and marked the screw holes with the pointy instrument by deeply poking holes onto it. And yes, we used a marker as well. Cutting the fibers physically was an extremely labor-intensive job since we had to put massive pressures into the plate with carbon knife and keep making incisions until it comes apart. Later, we needed to file the edges in order to make it smooth. This whole process was to be repeated again and again until we could carve out the whole required piece from the whole fiberboard. Today, we are taking up the drill machine. We have never done it before, so it was a first time kind of thing, but we were willing to learn. So after the main chassis piece was ready and cut out properly, we made sure the markings where we wanted the screw holes to be in the right position and brought in the lab's drill machine. A smaller drill lathe would have been better, but one we had would also get the work done. So yeah, with a little trial and error, we got it to working. It was such a fragile piece of material, so we had to be careful while making the holes and of the table underneath it. We don't want to punch tunnels on the lab table, do we now? After the holes were done, we could easily attach the battery holder and the driver module. The next step was to attach the DC motors onto the board, and it was tricky since there was no way to screw it on. So we took a file and brushed off some section on the laminated fiber. I'm talking about giving it a rough texture. Thus, we would give us the ability to hot glue the motor in place because it was so smooth earlier it wouldn't work otherwise. Now, we didn't get much of an assurance in that department because with the rough usage it may come off, not to mention the heat these motors would generate. So we took some zip ties and tied the whole thing in place on top of the hot glue to make it extra secure. It took some time to get everything in place, and after fiddling around for an hour or so, it was finally ready and good to go. Looking at something like this come to form is so satisfying, and it felt really good. We made a car from scratch, even the chassis. It was incredible. So our car had its form at this point, but it had no engine, so we needed to put one in. Now we decided earlier we wanted to power it with an Arduino Nano due to space and weight constraints, so I brought that in. Meanwhile, we took a bold decision and decided to make everything on mini breadboards and with prototyping cables. This would let us easily change things if something went wrong, and it would also be convenient for upgrades. Everything aside, it was actually a prototype, so why not use a prototyping board? So yeah, I made all the connection between the motor driver and the Arduino and wanted to try it out. That meant it was time to code. Now, we knew the code was going to be huge. All these different systems interacting with each other and working together. Not to mention, me and Sayanti had to share code with each other, and we needed a unified workspace. So we turned to the infamous GitHub, where we both created our own shared repository and got to work. We already interfaced the motor driver back in the lab to test it, so we just needed a fresh and optimized version of code rewritten to work with the full setup. So it's GitHub. Sayanti wrote me the code, and I brought it in, tweaked it a bit to match the scenario, and this little code was for testing out whether the wheels work and the motor driver functioned as intended. And it did. We were really happy about it. But now it was time to move on an inch closer towards the final structure of the robot. Here's the plan. Let's have two breadboards, one on either side, housing the Arduino Nano in one and the components like the magnetometer, DHT, the smoke sensor, etc. in the other. We'll bring the power back from the motor driver, then we can distribute it here in front. We'll have lots of cables to do that. So we got these mini breadboards, which are absolutely my favorite, so cute, and attached it in their designated position on both the sides. We already interfaced the Arduino with the motor driver, so we just needed to fill up the other breadboard. I started by adding a little buzzer and connected it with the Arduino. Day 5. It was the college fest. In the morning, we were busy interfacing and testing out the magnetometer in the robotics lab.
I guess you're back. Are you gonna tell me where you went? All the messages I sent with no reply. It's like that. You're just gonna walk into my room. I hate how you assume.
And the reason we had to use a magnetometer in this project is because we knew we planned to make a digital twin of the scanner unit in our mapping software. Now, a digital twin is a digital copy or instance of a real-world object. Wherever it moves, rotates or scans, we'll be able to see it in real time, updating in our visual display unit. So, in order to track the orientation and the state of the scanner unit, we had to incorporate the magnetometer. Getting the code to work on something like this was really tough. It needed some extra effort before it finally worked as intended. And now finally we could track the orientation and see it updating on the screen in real time. That was so satisfying. But little did we know, getting it to work with the whole thing was a complete different story. we already had the code for the temperature sensor up and running. So the only thing that was left was to interface and connect the DHT on board. So I did exactly that and tested it out to make sure that was working fine. But now it was time to interface the magnetometer. Since we already knew what connection worked the best and already had the clean code because of our rigorous testing back in the lab, we could now just fuse it with our current state and move on. The magnetometer lay horizontally on the breadboard when we put it in. Just had to make sure it always stays exactly level with the ground to avoid any miscalculations. As mentioned earlier, our deployable unit, which is our scanner unit with wheels, would scan the area, record the data and send it wirelessly to the receiver module, which will be sitting still and would act as a receiving and decoding station for the visual display unit or the software. Thus, we needed to get the wireless aspect of the project sorted out. To enable wireless communication, we decided to use the NRF radio communication model, which were really tiny and used SPI communication. So without any further ado, we got to work and quickly interface the module with the onboard nano using long wires, since I had plans to attach it to the approximate middle of the robot somewhere. After writing the code, we cleaned it and optimized it a bit and used my Arduino Uno to connect it to the second NRF module so that we can communicate with each other and test out whether it even works. The connection was a bit unstable and things acted a bit unreliable, and even after fiddling around with the data sheets, it wasn't much clearer to us. And I may have fried the circuits totally forward. It was a max 3.7 volt little module. Anyways, in order to take a break away from all this, I continued to work on a different aspect of the project, and that's the motor speed and duration calibration. You see, I needed the unit to turn approximately 90 degrees when the turn command is given, and in order to ensure that precise control, it needed to be calibrated. Luckily, we have that onboard magnetometer which tells us exactly how much the vehicle actually turns. So we took numerous amounts of readings multiple times. The unit would be commanded to rotate 90 degrees through an internal calibration routine made by us towards a specific direction, where the Arduino sends specific signals to the motor driver repeatedly and record the actual rotation that the vehicle undergoes. This rotational movement happens continuously, and the recorded data, which are the expected movement versus the actual movement, gets sent through serial communication via the USB cable connected. Through different experimentations, we noticed that different rotational angle descending uniformly gave the best amount of variance we needed to formulate the equation that we wanted. That is the reason why the robot tries to rotate a different amount in every iteration for our ease of calculation. This reading is taken again and again for numerous iterations and recorded for calculation. We then take these readings and bring them into Excel, where the best method we found was to plot all the average values and their relations and extract an equation out of it, which we can later use to calculate the exact motor speed and duration it needs to turn in order to rotate X amount. And now our vehicle could actually traverse and rotate in a precise manner. Any further imperfections won't even matter because we'd be able to detect the orientation in real time using the magnetometer. But it sure didn't go haywire while rotating like before. A fresh day, a fresh start. It was time to finish what we started. I dug deep into the wireless connectivity problem. I fixed the wires, thought that's what's wrong, dug deep into the code and the workings of the NRF and tried to operate it in an extremely high power to ensure proper stability and reliability. I even ordered a better, stronger version of the NRF module since I doubted the old one got fried. Since I found the model to be so sensitive to small voltage fluctuations, I gave it a little stability using a capacitor, and it seemed to hold on pretty well. With this done, I improved the wiring a bit, and all I could do is to wait to get other components delivered. It's always fun to unbox new stuffs. Apart from a big Metal Gear servo to house the scanning head, the variation in zip ties would help to secure the wires perfectly in place. Not to mention the multimeter that can be used to further troubleshoot the problems that I was facing. And though I almost missed the smoke sensor, it was a crucial component of the project for obvious reasons. The new NRF module looked so cool, like a Wi-Fi antenna. But before I could install that, I needed to make sure the whole setup worked as is at the moment. But I needed to have a formal way of communication between the software and the scanner module via the receiver or the broadcasting ground module. So in order to solve the problem, we needed to come up with a language of communication, a programming language like SARDA would understand when spoken to it. Thus, we created the SARDA programming language exclusively for this project, with which we could communicate and control the scanner unit vehicle, where the ground unit, or one can say the receiver unit, acts as a compiler which compiles the program code and sends the machine code via radio communication so that it can understand and act in accordance with it. With this simple decision, we had taken platform independency to a whole another level. We can have any OS running our software parallelly and can communicate and control the whole setup as a node with zero hassle. Before we move on, I have to mention that I integrated the smoke sensor as well on the second breadboard, where it fit beautifully, and when the need arises, it will give us informations like the amount of smoke a hypothetical fire is causing, whereas it's harmful for humans to breathe and more. With the new NRF module, a ground receiver was long overdue. So I brought some of those lamination fibers and started working. First of all, I measured and calculated how big and in what shape I wanted my ground receiver to be. After doing that, I used a pencil and a carbon knife to make the markings, which was followed by the traditional way of cutting such materials. I used the carbon knife to cut the lamination fiber in shape precisely, and even got some small pieces in order to make a small little tower to house and support the antenna of the new NRF Plus module. This would make it look like a Wi-Fi router. When I was finished with everything, I joined all the little pieces together with industrial glue and attached the NRF module with the antenna pointing up to the sky. With this done, it looked just like a DIY homemade router, as I stated earlier, and I was really happy with it. I used my Arduino Uno to power the receiver and the transmission process because it was big and there was lots of space in the receiver unit for the Uno. I used the jumper wires to connect everything and uploaded the code to make sure whether it worked as well as the previous installation. So now with the stationary ground module communication up and running, which looks surprisingly good by the way, it was time to fire up Unreal Engine in order to develop our software, aka our visual display unit. Now at this point, we had our magnetometer, our wireless communication, and the compiler or the ground communication module up and running. We just needed to be able to send commands not by hand typing them that we were doing earlier, but through the software that we developed. I needed to set up the codes for a serial communication network and the software and the ground communication unit. So I started working on the Unreal project. Before everything, I needed to set up the codes for serial communication between software and the ground communication unit. Here's the plan. We send a command in our own programming language to the ground communication unit that we just made. Let's say we request to get back the current orientation of the vehicle. So we send the code through serial to the Arduino Uno, which then compiles and sends the respective command to the scanner unit through radio communication. Next step, the scanner unit sends back the magnetometer reading, which is received and processed by the ground communication unit through radio and then is sent back to Unreal through serial. So now those of you who don't know, I already did something similar in my previous project, Armball Mania. Check that out if you haven't, by the way. A little sneak peek, a better and improved version is under the works now. So I ported that project and modified the code in order to work with the current one. Now for reference, I had a simple cone at the current moment just as a placeholder to check whether it worked and updated the orientation in real time on the screen as we rotate the scanner unit by hand. Turned out pretty well, but of course I am planning to change stuffs around to make it better. I have to overhaul the whole system to make it, as I said previously, more reliable. For the future, I had plans to wrap the data exchange in a JSON package, which would make it a lot easier to extract and exchange multiple information later with ease. But that was a problem for another day. This was a big day. I was super excited to get done with the hardware part of the project. I already had bought a servo and had two ultrasonic sensors in my arsenal. One was mine, one was Sayanti's. So before we could make the whole scanner contraption with two of the ultrasonic sensors, I needed to get the servo fixed. And if I didn't mention it earlier, I was planning to incorporate two ultrasonic sensors on the scanner head, each facing the opposite direction. This would allow us to scan all the four directions with a 90-degree motion. So I tested the servo and hooked it up with the main power source. Since this baby needed lots of juice, the servo needed to be calibrated in order for me to find out the zero position that it'll rest in. So after a little more test here and there, I hot glued and attached the servo with this chassis, and even this was not enough and it didn't even look good. So in order to support the servo, I used my good old lamination fiber to cut out some carefully designed pieces and attach them on either side of the servo. This would support the servo and hold it in its position. We needed another such structure to hold the two ultrasonic sensors in place. So I got to work and designed a U-shaped contraption that would hold the ultrasonic sensor in its place, which I attached and screwed in with the servo before sealing it off with another thin support bar. Getting the ultrasonic sensor fixed in their position was a messy job since I only relied on hot glue to hold it together as it solidifies. But somehow with all the strain and pressure, it kept crumbling down. Thus, in order to fix it, I needed to install another supporting thin wafer to push both of them apart and keep them from crumbling in. After fixing the structures with the servo, I just had to connect the wires flowing from two of the ultrasonic sensors to the Arduino. Which wasn't as easy as the others because the wire had to be of optimal length and specific tension, which would allow the whole contraption to rotate freely and not put much stress on the servo. But it should be hanging with enough tension so that it doesn't fall back and block the view or get winded up on the whole thing.
Sun's about to go down. So what you doing tonight? It's everything I can't think of.
But something weird happened. While testing the magnetometer, it seemed to act really strange. When the sensor is rotated in a constant motion, the rate at which the values change accelerate and decelerate in a vaguely unpredictable way. In other words, it was acting differently and was not giving the expected values. So I used a mapping program to randomly record some values to better look at what was going on as I rotated the sensor in a spherical manner. And I got what I feared the most. All the mapped values was skewed away from the origin where it should have been. Maybe because the magnetic field of the surrounding components interfered with the sensor, or maybe something else, but we knew how to fix it. We needed a calibration function, which we calculated with a handy utility. After so-called calibrating the sensor by running it through our fix function, which ran the old values through a calibration matrix, all of the strangeness was fixed in a blink of an eye. Now, the compass or the magnetometer was working as intended, perfectly, even when it's on board. Apart from all this hassle, I spent lots and lots of time managing the wire properly, tying them up with zip ties so no amount of stress or tension may cause loose connection or disrupt the proper functioning of the whole system. Since this was a project wholly on a prototyping board, this was crucial, not to mention the matching yellow tapes I placed later to make it look better and also for added support. I also took some time to add fully functioning joystick. But why the joystick? Well, as I stated earlier, we would be able to control the scanner unit directly from the visual display unit or the software. But still, in case we needed a manual override, we could just switch the mode and gain control of the vehicle with the joystick. Thus, I soldered the main switch with a little help from my father. Placed the joystick as well as the buzzers and the LED light to better indicate the status of the whole process. Also to help debug the whole thing if need be. With the hardware part almost done, it was time to focus on the software part. Since that was the most unique part of our project, the software interface, the way we would provide, will be extremely easy to use and modern in terms of UI and UX. Not to mention the way we will represent the data would be the most fantastic aspect of this project. That's what the goal was. Thus, I continued where I left off previously and started working bit by bit towards a bigger picture. At first, I needed to get the JSON done. Serializing and deserializing JSON string was a tricky job. We needed to serialize JSON strings, as I said earlier, back in the Arduino Nano of the vehicle, which means we needed to pack all the necessary details and make a JSON string so that we can transfer it wirelessly to the compiler or the ground module, which in turn sends the JSON string through the serial communication to the computer, which is the software. But that's not all. We needed to convert the JSON string back into a structure. In other words, we need to deserialize the JSON string and extract all the information from it. For that to happen, we needed a function which would handle the extraction in an easier way, as well as be fast while doing so. That is why at first I got to work in order to build such a system. Once done, I could easily check in our programming console window. Since we built a different programming language for our project itself, we can send a comment and the vehicle would automatically perform all the motions and everything necessary to scan and collect all the data at its present location. Build the JSON string and send it to the computer in order for the software to represent it. The representation that I needed to work with before anything else was the pillars. As I said earlier, the pillars are the unitary 3D structures that the software uses to build the 3D environment. The more close it is to the scanner, the bigger, and the farther away, the smaller. To construct such a structure, our digital twin on each tick requests a JSON package with all the necessary environment details to build a pillar. It creates a new instance of our unique pillar object and calls custom constructor, where it sends all the information that it unpackaged from the JSON package. This constructor handles all the rendering and animation work itself, which I'm not going to go into much details at this moment because we still have work to do. We need to build a world, a sandbox. This is my favorite part today. I'm going to work on the visual aspect of the software. Now, I absolutely love game development and game design. Apart from that, I have made several 3D artworks previously. So this is the part which I enjoy the most. This was a technical software, and most technical softwares are boring looking, but not us. We're going to make it modern and beautiful looking as my other games. So for the look, I wanted this really pure, white and well lit and empty space with grid lines on the floor, where all the pillars and our digital twin would cast really soft shadows, and it would give us that soft, well lit professional look that we're going towards. Most softwares I have seen has really old-fashioned 3D renders, but we are going to make the shadows and the lighting super accurate and super smooth. And the way we are going to achieve it is to implement real-time ray tracing into the project. I'm talking about fully ray-traced shadows, fully ray-traced lighting, along with 4K textures and high polygon models. And it was a long journey. I designed the model in 3D Studio Max and brought it in the Unreal Engine in order to texture and animate it. Now the environment, it took a lot of time. I experimented with different parameters and the directional light in order to get that soft look that I was aiming towards. The grid patterns was custom made in Photoshop, so we could change it anytime, and I did go through different variations throughout the project. I was working on it in order to get that look which I was going for. Once the environment was done, we needed some way to control the scene. The user needs to be able to rotate and look at the scenes from any point of view. They can even zoom in if they want to. And if they leave the mouse button, camera would come snapping back into the position where it is best fitted to view the digital twin from, which it is paired to. This would kind of convert our software into a full-fledged 3D software, because the controls are exactly like a 3D software, say it AutoCAD, 3D Studio Max or Maya, where we had taken inspiration from. Now, I had never worked on such intense camera controls before, so it was a lot of experimentations that needed to be done. I'm talking about nights and nights of working along stretch hours in order to learn and experiment with the camera. I'm not going into the details of what happened because, like I said, it was a long journey. I went all in with the animations. Now, just like the camera controls, animation was not my strong point, so I had to learn a lot of different new things in order to pull it off. I won't go into much details, but for the animation, I wanted the pillars to appear from nothing, as it would scale itself up in a really unique and animated way, which would look really good. I worked on it so much to get the animation that I had in my head. Not to forget, the color changing features of the software also falls under animation. What the feature actually is, that when a pillar is drawn or animated, the color which it emits from the edges changes, which is pure white initially, changes over time into red to showcase that enough time had passed in order for it to be an outdated reading. Yes, I meant it when I said our software was going to have some really unique presentation techniques.
I never know how I'm stuck and left alone.
After everything had been done, I needed to change the way our digital twin was represented. It was really old-fashioned and outdated because it was actually a placeholder for what we would be creating later, and it's already time to make that happen. So I fired up 3D Studio Max and designed a new one. This was going to be the main center of attention, so it needed to be elegant and good looking. After coming up with the proper design, I brought it back into Unreal, textured and made it a bit illuminative to proper match the feel of the environment. After I was finished, it looked really good, matched with the color scheme, and thus we were good to go. At the end, I brought in a post-processing volume in order to add that sweet touch of color correction and color grading to give it that spicy look. I actually made the lookup table in Photoshop from scratch only for this project in order to achieve the custom look that I was looking for. Everything had been done at this point. It was now time to add buttons and the way for the users to control the software. Also the heads-up display, which would display the informations about our digital twin on screen, like the temperature, smoke, humidity, and the orientation data. I wanted all the environmental data to be displayed on the left on floating islands and the orientation data in degrees at the top. Not to mention, all these data are also, as I stated previously, displayed on a floating HUD UI on top, attached to our digital twin, so the user doesn't have to take their eye off it ever. That's called juicy UX design. So as usual, I fired up Adobe XD in order to design the user interface. It was early August. I was working on the project, perfecting and improving the way the whole system worked. And yes, working on the visual and technical aspect of the software as well. When I received a call. We were invited to this National Science Fair exhibition at the end of this month. where we were to present our projects in the university's booth. I mean, this was a huge deal for us. So, with the strict deadline of almost a couple of weeks, we began rigorously testing the bot, since almost everything was done at this point. Here's a little tech demo where the scanner unit path finds through my room and beautifully maps everything, where the height of the pillars inversely denotes how far the scanner unit was when that specific pillar was mapped, and the dynamic colored lights on the pillar changes to denote how old the mapped pillar really is, not to mention the temperature, humidity and the smoke data written on top of each pillars. So yeah, that was the project. It was time to brush everything up for the last time and wait for the big day until it finally came. It was a day, not gonna lie, we were somewhat nervous since it was kind of a big thing for us, but we did our best to give them a show. Apart from SARDA, we also presented our previous project, that is Armball Mania, and the crowd was insane. We had the booth to ourselves for the day, where we had all the working units of SARDA displayed clearly in front of us, with the full power throughout the day. Even the visual unit was working on the laptop. The exhibition was filled with young kids from all over the city, from different schools, different backgrounds, and making them understand the working of this robot, about what makes this unique. Presenting them the new ideas was really satisfying, and we enjoyed it so much throughout the day. From different army personnel, professors and other members from the upper echelon of the educational circle. But after a whole day of work and presentation, when the day came to an end, we were finally awarded with the grand prize for our effort. The whole experience of presenting our hard work project was something that was truly unique, and we learned a lot from it, and we were willing to do it again. So, with great trouble and great fun, another project and another year comes to an end. Our project here is done. We are going to move on and work on something new and exciting for the next video. Let's just say we have an unfinished work to do. Goodbye, take care, and as always, keep creating.
See the horizon, turn us to thousands, and we'll grow in number. Fueled by them to see the horizon, turn us to thousands.